Okay guys, we're back at it again. Day 3, we're dealing with concavity. So we're dealing with points of inflection. We had a little discussion about that already. And that is determined by the second derivative test. So if you look right here, second derivative test is right here where you take the second derivative and set it equal to zero. And where you find those x values for when the second derivative is equal to 0, you get where the concavity changes. Special note, the tangent line does not change sign for concavity, so or for the point of inflection. So we'll discuss that a little bit later. So concavity, if f double prime of x is smaller than 0, the graph of y equals f of x is concave down for that interval. And if f double prime of x is greater than 0, looking right here, the graph of y equals f of x is equal to, is concave up of the interval. If f double prime of x changes sign at point C, x equal to C, that is, the graph changes from concave up to concave down or vice versa, then this point right here is a point of inflection. To find the point of inflection, let the double prime of x equal to 0, solve for x, and then we do a nice ugly chart. So let's just chat for a minute. So I'm just going to do some rough notes. You can just listen. You can take a few sketches if you want. It's up to you. If we look, we have a point of inflection approximately right here. Give or take a little. I'll make it nice and big so hopefully I get the right spot. And if you look, we have two parts to the graph. This part here is concave down. Our point of inflection is where it switches to concave up. Okay. So if we went and did the first derivative test, we would have found that we had a max right here, and we had a min right here, because the tangents are 0. Now let's take a look at what's happening to the tangent lines. So right here, this is a really steep tangent, okay, like maybe 10. And then if we look here, it looks like it's about 1, so it's decreasing. And right here it's 0, which means it's still decreasing, because if you look, we went 10 to 1 to 0, that's decreasing. And if we look, keep on going, we've got another one right here. Maybe that's -1, still decreasing. And then we hit this one right here. Okay, so maybe that's like -1.5. So we kept on decreasing. +10, +1, that's a little bit smaller. We're decreasing. 0, -1, -1.5. That whole time it was decreasing. And then it switches. And then we start, let me grab a different color as we keep on moving. Let's say that is -1, -0.5, 0, 1, 10. And as we moved, all those numbers that I just listed, say -0.5, or -1, -0.5, 0, 1, 10, those all started increasing. So if you look, my tangent went from decreasing and then stopped and went increasing. And at that switch, we get our point of inflection. Well, if I went decreasing, I decreased, and then started increasing, that would happen at my second derivative equal to 0, which is what we're looking at today. If we take a look, this is our first question, and it is insane. It puts everything all in one spot. And we're going to go through and we're going to find the x-intercepts and we're going to find everything. But I can tell you it's a very long question. It's a very ugly question. So let's go through it and hopefully everyone's good with it. So we start off and we might add a few notes in here, but the nice part is most of it's already typed up for you, so you don't have too much to add. So if we look at this, we're first going to find the x-intercepts. So we've done this before. We did this back in higher functions. Just a format change. I like to say 4x-intercepts at y equal to 0. Then we end up with this. And we really don't like all those fractions here. See the 2, the 3, the 3. So if we go through and multiply everything by 6, the lowest common denominator, then we end up getting this equation right here. No more fractions to deal with. So now we have to go and do the long division thing, the remainder theorem, and the factor theorem on this equation right here, to try and factor it. So if we take a look, let's do it. We move over to here. we have to let this function be something, so we just let it g of x equal that function. And if you remember, we are looking at all of these subbed in. Now, how did I get those? Hopefully you remember. We were looking at all the combinations of whatever the factors of 10 are over the factors of 3. So we would be looking for, list out the factors of 10. So we would get 1, 2, 5, 10 over all the factors of 3. 1, 3. And they could all be, sorry my squiggle brackets look awful, all be plus or minus. So if you look, we tried all of them. We got 1, -1, 2, -2, 5, -5, 10, -10, 1/3, -1/3, scrolling down. Keep on going. 2/3, -2/3, 5/3, -5/3, 10/3, -10/3. None of them equaled 0, so we cannot do any long division on this. So it's not factorable. There could still be some x-intercepts. I don't know. We'll see when we're finished. But we can't find them easily. Everything in life is not easy, unfortunately. That's why we take calculus. So if we look, let's add in here to find the y-intercept. So for the y-intercept, set x equal to 0. Right there. And we go through and we get the y-intercept's 5/3. A nice, easy point. Awesome, now we have to go and do the first derivative test, so let's do that. So, we go and we have f of x, we just rewrote it. We find the derivative, we all did that last unit. Factor out of 2, oh look at this, it factors by grouping. So I can take out x squared out of this, and I can take out a -1 out of this, and I can factor by grouping, and look at that, that's a difference of squares, it's going to break off into those two factors as well. So that's fantastic. And then we set f prime of x to 0 so we can find our critical points. Sorry for the short forms, but I'm having trouble getting all the words in on the iPad. So if we look, we do that. It's already factored here, so we end up critical points could be at -1 or +1 and 4. So we'll go and do the chart for that after to find out where all the max and mins are. But I like to get all the derivatives out of the way first, so we're going to go and do the second derivative test as well. So we have the first derivative here, so go and take the second derivative. I can factor out a 2. This right here does not factor nicely, so I'm stuck doing the quadratic formula. So minus b plus or minus the square root of b squared minus 4ac, all divided by 2a, and it's all subbed in right there for you. Simplify down, and it's super ugly. That's okay, we'll go and put that in the chart as well. Now I've done this in 2 separate charts. I think Mr. DeGraff does it in 1 chart, and I'll show you how that looks at the end as well. But I like to do it in 2 separate charts. I do one for the first derivative test, and I do one for the second derivative test. So if you remember for the first derivative test, that would find us our potential max or mins, and we had our roots for that, for the first derivative test, x equal to -1, 1, and 4, and then we have all the ranges on either side, here, 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 and here. So you don't have to go and write those red marks, I'm just pointing them out. So we go through and we know at -1, we know the derivative is 0. So 0, same here, 0, same here, 0. And then you go and you pick some values for the intervals that are in between. So if you look here, this is for x less than -1. So you go, maybe sub in -1 into the first derivative and you find out we get a negative. Here you go and sub in 0 into the first derivative and you end up getting a positive. And you go and sub in maybe 2 or 3 into the first derivative and we get a negative. And finally maybe we sub in 10 into our first derivative and we get a positive. So that means it corresponds to decreasing, increasing, decreasing, increasing. Fantastic. If I go decreasing to increasing, then I get a local min. If I go increasing to decreasing, I get a local max. And decreasing to increasing, I get a local min. Sweet. So, the points that you have to have on here, you want to know where your local minimum or maximums are. So you're going to sub in that point. It's your x equals to -1, sub it into your f of x, and you'll find out where that y value is, or what that y value is. you do the same, sub in x equal to 1 into f of x, and you get this point for your local max, and you sub in x equal to negative 4, and you find out your y value for your local min. Fantastic. So that's the first derivative test, all done in this chart right here. Next, we're going to go and do the second derivative test. So if we look, yes, unfortunately, we need to be exact. We have these two values here. And the first thing I do here, I go and put those zeros in for the second derivative test because I know those right away. And then right away, I go and I figure out the points. So if you look right here, I went and found out my points right here. And the reason I do that is because at this point, you can go and change this root right here, or this x value, into a decimal right here. Okay? This means nothing to me on a graph. I have no clue what that number looks like. But that one, oh, it's close to 0 on the negative side. And this one right here, punch that on my calculator, and I end up getting 2.8. Fantastic. And then I go and figure out what the y value would be associated with that, negative 11.4. Excellent. And then I go and do my test points in my second derivative. So if this is negative 0.12, pick something that's smaller than that. So x has to be smaller than negative 0.12. So maybe you pick negative 10 and you find out when you sub it into f double prime it's positive. This one range right here, I pick an x value that's between negative 0.12 and 2.8. So 0 would be a perfect one there. You could choose 1 as well. You could even choose 2. And I find out that it's negative. And if I look at the last one right here, I pick something bigger than my 2.8, because remember this is equal to 2.8. So 3, 4, 5, 10, 100, it doesn't matter. It comes out to positive. If I have a positive second derivative, it means it's concave up on that interval. Okay, and we know we've already figured out that it's everything on the other side of this x value right here. So if my second derivative is 0, everything on the other side has to be positive because I did the test point there. And so if you look, negative is concave down, positive concave up. If I go concave up to concave down, I get a point of inflection. If I go concave down to concave up, I get another point of inflection. And that's fantastic. That's the key point here. Now, you might choose to go and pick some extra points. If you look, I did it in the first chart as well. Negative 2, I chose there and got 11. Something in here, so maybe a half. Something in here was 2 and 3, and I went and figured out those y values, and I picked some here. I probably have enough points already, so these are all just a duplicate there. Okay? If I need any extra at the end, I can just write them right down here if I need extra to shape out my graph. So let's go and put all of this information on a grid. But right before we go and graph it, I noticed an error that I need to fix, so nothing crazy. This right here should be negative 4.8. So let's go and write that in proper. And my penmanship's going to be horrible. Negative 1, comma, negative 4.8. We'll do that again here. Negative 1, comma, negative 4.8. Sorry about that. Now let's go and graph it. Okay, at this point, I want you to put a scale on here. I'll put mine on, and then you'll see it pop up, and you can do the same one. But I want you to think about what type of scale you're going to do first. You got to go back and look at the previous page, see what size points you need, what's your largest y value, what's your largest x value, and smallest, so that everything's spaced out nicely. So go look at those, pause this, think of how you would do your scale, and then compare it with mine once you unpause it. Okay, so looking here, I went and I had to make sure that I had enough space to hit a small y value of negative 25. So that's why I went up by 3s on my y scale. And I wanted to spread out my x scale as much as I could, so I went up every other one being 1, and that should fit everything. Well, we might have to cheat a little at the right, but at least it'll be nice and spread out. So now we have to go and plot our points. So go back and look at all those local mins and maxes. Go and put them on your graph, pause it, and then you'll see them match up with mine. So those are my maximums and minimums, local, all plotted in blue. So now go and put your points of inflection on. So go back to your second chart and look for your points of inflection. That'll tell you where we switch from concave up to concave down or vice versa. So go and plot those points and I'll do the same. So pause it. Okay, so I went and did those in red. Hopefully I have them right. Now we have to go and fill in some extra points. The reason we have so many extra points to fill in is because we tried to factor f of x so that we could find the x-intercepts. We tried to set y equal to 0 and then go and factor it to find out what my roots were, and we couldn't find any. The reason for that is we couldn't factor it. It doesn't mean they don't exist. Had we had a bunch of roots to go and plot, that would probably be enough to do a nice curve. But we don't, so we're going to go and pick some extra points to fill in the gaps. We can see right now the curve's starting to take shape. We have a minimum, which goes up to a maximum, and then comes back down, hit a point of inflection there, and then back to a minimum, and then it's going to skyrocket up this way. So let's just fill in some extra points so we get a nice smooth curve, and then we can connect the dots smoothly. Okay, so I used light purple for the extra points. I think I actually had a few more on there, but this should be enough to get your nice smooth curve. So we have this one way up here. That's going to come down to my minimum, and then I did my y-intercept. That's always a great one to plot because it's easy to find. I have one at 2, I had one at 3, I got my minimum at 4 already plotted, I have 5. We've pretty much done all of them, almost a table of values it seems, but at least we're a little more accurate, and we can use this general algorithm for any curve. And then after this one we went and found 6, and it was huge, so we know that it's just going to skyrocket off there. So that's why I wasn't too stressed about getting all the way over to a 6 on the x-axis, because it was, I think, 85 or 86, and we wouldn't be able to plot it anyways. So go try and do a nice smooth curve. Again, it doesn't matter that I use different color points. I just did that so you could see the blue ones were our local extrema, our red ones were our point of inflections, and my light purple were my extra points. You're probably doing them all in the same color because you can. So try and do a nice smooth curve. I'm going to pause it so that I can take a few goes at it because I'm not doing so well on drawing on the iPad. Okay, and there we go. So do your best to do a nice smooth curve. At the end of any curve that you sketch, you should finish off with what would Mr. Hetherington take marks off for. You might have already saw it or might have already put it on yours, but I need the x, y axes labeled. X and y. Oops. Now if you look on the next slide, I actually have the graph already done just so we can compare. Now realize it might be stretched out a little more. That's just because the scale for the graphing software did it a little different. No big deal. So let's take a peek. And there you go. So it looks pretty darn close. Maybe label the x and y axes on this. Pretty good. So that's about it. So I'm going to do a few extra scratch notes on the next page just to kind of solidify everything that we've done. I'm going to go through a quick example but not do the actual graph just so you get another idea of what's happening. So next slide. So what we've done today is we've been able to figure out where the graph turns from concave up to concave down. So let's put all of this together. Let's make up an example, so it's nothing related to the example we did. So if we had our coordinate axes, let's say I have the ability to find the x-intercepts if the factor theorem works. So let's say we picked up another one here. We could figure out the y-intercepts from last semester. So that's another piece of the puzzle. We now, with the first derivative test, could pick up the minimums and maximums, and we've also figured out now with the second derivative test where something might switch from concave up to concave down. So let's fix that. So this looks a little better there. So again, that's where things switch from concave up to concave down. So if you look, let's just draw it roughly. And again, you probably aren't copying this. This is just kind of collecting all our notes for the day. So this is where we go from concave up to concave down for that blue dot. So that's concave up. And this is concave down, and that's where it switched. Good enough. So we've put it all together. Now we're going to solidify this in an actual algorithm, but you got to think of how nice this is. We're just dealing with polynomials right now, and we've done that before. We've done rational functions before, and we had pretty good ones last semester. Now we can actually find the exact minimum, which is great because a lot of word problems could benefit from that. But you got to think, we've also have, and we haven't done them yet, trig equations, logarithmic equations, exponentials, where now, when we mix them all together, we have the ability to find out where they switch from concave up, concave down, and where they switch from where their maxes and mins are. So, yeah, I kind of haven't seen the full benefit of this algorithm yet, but when we apply it to the more difficult curves, which we will, it's pretty neat. So let's go through that quick example at the end. I'm going to say a thank you to Mr. Graf. He typed a lot of these up, and I've modified them for this software. So I'm going to show you one of his solutions. He does his charts a little differently, and you might like it. And if you like it, go for it. I find them a little more confusing, but to each their own. I think some people might like it better because it's all in one spot. So let's go through it. So here's a quick example. I know when you look at it, so much, but don't worry, we'll run through it together, and I'll put little arrows so you can see how it flows. Again, we go through, we find our x-intercepts. So right here, I probably would have said, find the x-intercepts at y equal to 0. We go through, and it looks like it does not factor. So right here, he's doing the remainder theorem to see if we can get it to be 0. It isn't, so we can't do the factor theorem. Unfortunately, so that's all right. So then he goes to the first derivative tests here. So he gets the first derivative. He factors it. He sets f of x equal to 0. And he ends up getting this could be 0, or with the quadratic formula, that could be 0. And there you go. You have possible critical values there. Sorry, I forgot to mention way up here. This is where the y-intercept is. So that's nice. He's done his rough work right here for figuring out how to factor this. And then he does his second derivative test way over here. And when we set the second derivative to 0, we pick up these points right here, which are possible points of inflection. And then we put it all into one chart by itself. So this is where I find it a little more confusing, but lots of people like it because it's all in one spot. So if we take a look, you have to put everything in here. So if you look, you have to list all your x values, your local minimum, your local maximum, your possible points of inflection. So if you look, we've got, using my laser pointer, we've got -5, we've got 1, we've got -5/2, 4, and 25/4. So if you look, you have to put them all in order. We got -5, -2/5, 1, 4, and 25/4. You list all of those, and in between you get all your intervals. So that's the end interval, 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 and then right here is where we do our first derivative test. So if you look, we are more interested in all of the x values that happened here. Okay, so x equal 5 was an important one. We get 0. X equals 1 is 0, and 25/4 is 0. And we really don't care about this one and this one because they were associated with the second derivative test. Positive, negative, positive, negative. And then that would result in a local max here, a local min here, and a local max here. And then right here we're doing our second derivative test. So those are centered around these x values. So here and here. You do a test point, negative, it's concave down, positive concave up, negative concave down. And there you go, and you have all your points all nicely arranged right there. If you look right here, local maximum, point of inflection, local minimum, point of inflection, local maximum. And then in between, you have all of your extra points that might help you out. One here, 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 here. So everything's all in one chart. I might ask you tomorrow which one you like better, and we can kind of work from there if you like it. I can tell you this right now. You will probably have to look at this chart if you choose to do it this way, while you're doing your first 3 or 4 graphs, just to kind of get the idea of how it's set up, and that's totally fine. You'll probably have to look at the 2 separate charts as well, just to see how it's set up. You take all this information and you plot all those points. So then you take all your information and plot it on this graph. So you would have plotted your maximums, your minimums, your x-intercepts, had you had any that you could find easily. In this case, I don't think there were any. Your y-intercept. And then your points of inflection, which seem to be right around there where it cuts to concave up to concave down, and in and around there. So you would go and plot those points. And then all your extra points to help you get the shape. And if you see, when you graph it, you can see right here, concave down, concave up, concave down. There you go. So everything all in one spot. So we'll probably chat tomorrow to figure out which one you liked better. Again, a huge thank you to Mr. DeGraff, because he originally typed up this note and I modified it for this application for the iPad. So have a good night, guys. See you tomorrow.